Have you ever wondered about atoms? Like how big an atom is, or more accurately, how small? Many have wondered this, but perhaps not so many have a sense of just how many atoms there are, and even something like this. How many atoms are there in this? That's what we're going to answer. An atom is profoundly small, and in this illustration we will see just how small it is. But first, we're going to have to take a look at just what atoms are, and there are many misconceptions about this, and explain some difficulties in determining their exact size. The following is an illustration. It is composed, as one should know, of a nucleus to which is affixed electrons. The nucleus is actually much too small to represent on this scale, but we show a small dot in the center. The diagram we show here shows an atom of hydrogen. There is one electron and one proton. The electrons don't have any particular position or pattern of movement in space, at least not according to common interpretations of quantum theory and the standard mathematical model thereof. Rather, the electrons have something else. Wave functions, and these wave functions achieve their maximum amplitude in the area occupied by the atom. The electron wave function takes up the bulk of the atom. The proton has a wave function as well. No, it gets even better than that. But that's more complicated than I want to get into here. This is still a pretty good model. It's even now not perfect, but it's much closer to the truth than this. Don't fall for that one. Admittedly, though, what exactly these wave functions mean on a deep level, quote, in the real world, end quote, is subject to a lot of yummy controversy. As we said, this is complicated, and we won't get into that. Simplest, honest, and least presumptive way to understand it is probably just that it's how the mathematics of the theory describes the electron. Nobody can really disagree with that. And it serves well enough as our best visualizable picture of what an atom, quote, looks like, end quote, however you want to imagine that. The atom behaves, at least modulo caveats and caveats, like it is a ball of about the size shown from this wave function picture. It is important to point out there is no hard edge. In fact, the wave function does not extinguish as one gets further out, no matter to what distance. Even kilometers away from the atom, in theory, the wave function is not zero, but nonetheless has shrunk to an incomprehensibly small value. Thus we cannot actually define a boundary of the atom that isn't, to some extent, an arbitrary construct. Nonetheless, however, there are three basic approaches to choosing what to call the, quote, size, end quote, and we overlay them atop the picture as thus. As you can see, the largest radius pretty much contains all the visible wave function. For a free-floating hydrogen atom, the usual one to take is the largest, called the van der Waals radius, which represents the radius at which another hydrogen atom approaching it would undergo a collision. This radius is 120 picometers, so the whole atom is 240 picometers across. For two hydrogen atoms bonded in a molecule, the smallest one, the covalent radius is one often used, which is roughly the distance from the center to the middle of the bond. When bonded, the two atoms, quote, hug, end quote, each other rather more tightly than just in a glancing blow. And when that happens, the wave function also complicates, and it can't be so easily pictured as shown here, although there are a number of approximate constructs that could be more easily pictured. The middle circle is the Bohr radius, which was the radius of the atom as imagined in the old model of Niels Bohr, similar to the awful one we just showed, but a little bit better. Now, how small is this 240 picometers? If we expanded this atom so that instead it were 240 micrometers across, just barely visible to the eye and around the thickness of one of the markings on this ruler, the entire object, this, would expand from its current size, about 188 millimeters, to a size of about 188 kilometers in length, enough to stretch across much of the state of Massachusetts in the USA. Or for a more international audience, the width of the nation of Italy. We wish to apologize. We believe that the world should be fully metric. We're not going to use old units based on dead king's feet or dried up cereal to measure things, especially not kings of the majority of people who still use such units now swore as their enemy a long time ago. For most of those who are still using such units, this illustration should be perfect to tell you all you need to know. Laid on its side, this thing would be 7 kilometers high. There's no mountain on Earth of prominence as great as this object would be. To climb it would be suicidal. It would have an overhang extending for 3.5 kilometers, unless you climbed from the flat end. To walk its whole length would take a human, without rest or sleep, walking at a typical pace of 1.4 meters per second, about 130 kiloseconds of uninterrupted walking, which comes to about a day and a half, with no sleep. There are people who commute this distance, and more, to and from work every day. That is, they drive by what is in effect one or more of these inflated atom piles each and every single day twice, spending lots of kiloseconds out of their day just to travel the same route over and over again. There's only 86.4 of those kiloseconds in a day, and people may work for 30 of those kiloseconds or more, and we need sleep. Do you think there's something wrong with this world? Do you have any stories of long commutes to lighten the atmosphere here and simulate interesting conversation? We can make videos on all these subjects too. You can guess then that the atoms in this object must also come in immense quantity. Given how small they are and how vast this thing is, how many are there in the object? The exact amount cannot be known, of course, but it's not hard to estimate it. If we just consider that the object is a cylinder with a radius of 3.5 millimeters and a length of 188 millimeters, we can get its volume as 7,235 cubic millimeters, give or take a few due to measurement errors. To get the number of atoms, we must next have an idea of what types there are within it. To get a not unreasonable model, we can assume that it contains the inner cylinder of graphite with a radius of 1 millimeter and the rest wood. Using the same formula, we can get this inner cylinder as a volume of 591 cubic millimeters. Thus, the volume of each part is. With that, we can now estimate the atoms. Wood is, of course, a complex set of molecules composed of many different types of atoms, and bonding between them complicates things significantly, but we're only interested in the rough model. What we need is called the molar density. The molar density is essentially how many atoms or molecules fit in a given volume. They can be obtained from regular densities by dividing the ordinary densities by the molar mass, the mass of a standard quantity of atoms, called Avogadro's number. These units of atomic count are called moles, a standard unit in the SI metric system. The composition of wood is about 50% carbon, 42% oxygen, and 6% hydrogen by mass, plus 2% of other stuff we'll just leave off for this crude calculation. Thus, 1 milligram of wood contains 0.50 milligrams of carbon, 0.42 milligrams of oxygen, and 0.06 milligrams of hydrogen. We can now use the molar mass of these to find the total number of atoms in millimoles. Adding those up gives 0.13 millimoles in 1 milligram of wood. The density of the wood is not certain, however, which we need to get the molar density of atoms, not molecules. Looking, however, at a wood density table and using the made in China, this author guesses the density is 0.7 milligrams per cubic millimeter. Thus there is 0.09 millimoles in 1 cubic millimeter. This is the molar density. For solid carbon, a similar calculation yields 0.1888 millimoles of atoms per cubic millimeter. Note that we lost a lot of precision. The least precise figure was the density of the wood. Now we need to multiply that 0.7 moles by Avogadro's number, about 6.02 times 10 to the 23rd, to get the total number of atoms in this as this. Now, how big a number is that? It is read as 400 sextillion, or to use the long scale system of numbers common in other European languages than English, some equivalent of 400 trilliards, which arguably sounds much cooler. It's fun to note there's a legendary story in the Indian Buddhist tradition where the Buddha was said to have been challenged to count the number of atoms in the yojana, an old Indian measure about 10 kilometers at the time, though the story dates from later than Buddha's own time apparently. He said it was around 100 trillion atoms long, giving the size of an atom as this. While not totally accurate, it is nonetheless the right order of magnitude. Make this what you wish. No doubt many state a guess at the size, and someone had to be right. But nonetheless, it shows people have been thinking about atoms for ages before they were actually discovered. In fact, the idea of atoms was proposed independently in the ancient world by two thinkers living thousands of kilometers from each other, Democritus in ancient Greece and Kanada in ancient India. As to who was first is debatable. But this gives us an idea. What if we took all the atoms in this and laid them all out end to end in the matter of that story? Using the proportions of millimoles of different kinds of atoms in our milligram of wood and the unbounded atomic radii, we get the average size of a wood atom is about 143 picometers in radius, or 286 picometers in diameter. The carbon atom is 340 picometers in diameter. Averaging these in proportion to the number of atoms in wood and of carbon each in the sample, we get about 290 picometers for the average of an atom of the object. Thus, using our 400 sextillion atoms, we get the length as 100 trillion meters, also known as 100 terameters, or 100,000 gigameters, where the gigameter is the most convenient metric unit for measuring distances within the solar system. We'll leave it to you to know how many kilometers that is. Yes, if we strung out every atom in that thing, it would stretch out far past even the distance Voyager 2 has reached, the furthest human-made object has been sent from Earth, to make it perhaps even a third of the distance to the beginning of the Oort cloud, according to low-end estimates, the vast cloud of comets that forms the borderland between our solar system and the great beyond of the galaxy, the place beyond where the map runs out, and there is only written a chilling warning, here be aliens. At this scale, our map of the solar system must zoom so far out that we cannot even see the familiar planets. To walk that distance at 1.4 meters a second, equivalent to 1.4 gigameters per gigasecond, it would take you 70,000 gigaseconds of walking. For comparison, the longest-lived human to ever live, John Calment, only lived for a bit under 4 gigaseconds, or 122 years. You'd have to live over 18,000 times longer, and to be wholly incapable of tiring, a human perpetual motion machine par excellence to achieve the feat. While you did so, empires would rise and fall, and whole epochs of history would be made back home on Earth behind you. In fact, 70,000 gigaseconds comprises a very large segment of the timescale of human evolutionary history, going back all the way to the emergence of genus Homo, which includes all the most human-like ancestors of today's human species. Could these be somehow so immortalized, people back home, if there are any left, would probably not look like people anymore. And remember, this is the atoms at their actual size, not their inflated size. There are so many that even at this incomprehensibly tiny scale, they stretch out unimaginably far. This also illustrates yet another vast scale we should explore, the scale of the universe in rather somber terms. That is a topic for still another video. It is most wonderful how, in the great abundance with which atoms abound all around us, the scales of their immense smallness in inner space and the scales of the immense grandeur of outer space find here their union. I hope you share in the awe that I feel for this once most amazing thing, and also in the sweet wonder of how naturally it arises in this exercise. But the longest time of all would be that if you were asked to arduously count the atoms one by one. If you counted one per second, again as perpetual motion with no rest, that would take 400 sextillion seconds. There is a prefix in the metric system for this. We would say it is 400 zettaseconds, or for comparison, 400 million petaseconds. The universe's age, by contrast, to 13.8 billion years is only around 430 petaseconds. This means that the count is around 1,000,000 times longer. The whole universe would have grown dark and cold, with even the most feeble of stars giving out long before you exhausted the pile of atoms and completed your task. Much like another famous story of Buddha, where he was said to have claimed the length of one great cycle of the universe as being even more than the time it would take you, were you to withdraw from a great cube 1 yojana on a side brimful with mustard seeds, one tiny seed every 100 years, for the entire cube to be brought to a vacuum. And with that, we will see you later, and hope you keep making sense of what's out there, and hope you love our universe, and also love the person next to you, if there is one there, or your pet animal, if you have one cuddle on your lap. Give it a little kiss. We need more love in the world, and less hate. And then tonight, or whenever you can, go out and look up at the very large. Then look at your hand, and think about all the atoms that make up you. How big must you be compared to them? Then think about how big the universe is compared to you.